Continuing on from chapter 1.6 part 3 on factoring polynomials, our goal is to factor 12x3 minus 6x squared minus 6x completely, such that when we have the answer, we can multiply it back to get back the polynomial. So I'm going to list out the factors of 12 that involves 6 times 2. And it seems like with the x3, we can lay out the 3x's. And going to the second term, we have 6 and then separated by 2x's and then 6x. We can commonly see that 6 exists in all three terms. I'm going to pull it out from the parentheses. And the same thing goes for 1x. I'm going to pull that outside the parentheses. Everything else that we haven't touched will remain inside the parentheses. So that's 2xx, which is 2x squared, separated by the minus sign. It's x, separated by the minus sign. And since the fact that we pulled out the 6x outside the parentheses, it becomes an identity. So therefore, it's going to be 1. Just to confirm that, when you distribute 6x to all three terms, you can see that on the last term, 6x times by negative 1 will be negative 6x. But we should be a little bit suspicious about the terms that's inside the parentheses. Using our knowledge from the previous video, we can see that with the polynomial leading coefficient of 2, we can use a chrysalis method to find out if there is a factored version of the polynomial. So I'm going to put 2 on the front. Multiply the beginning times the end, so 2 times negative 1 is negative 2. And the middle term, which is negative x, goes at the bottom, so negative 1. And now you want to ask yourself this question: what are factors of negative 2? So factors of negative 2, that adds up to negative 1. So if we want to lay out the terms, 1 times 2. And since the fact that one of the numbers must be negative, I'm going to maybe just put a negative 1 there. But we can also do it the other way around. And again, we want to find a sum to give us the bottom number of negative 1. So negative 1 plus 2 is 1, so that doesn't work. And then 1 plus negative 2 is negative 1, which works. So I'm going to put 1 and then negative 2. Treat 2 over 1 as a fraction. This is already simplified, so therefore we can treat it as 2x plus 1. Now, as for 2 over negative 2, we can see that we can divide the 2 on the top and the bottom, which is 1 over negative 1. So in the parentheses, it becomes x minus 1. When you think about it, it's 1x minus 1, 1 over negative 1. But granted that 1 times x is just x, so we can just keep it like this. And we're going to keep the 6x on the front, so don't forget about that. So 6x times by 2x plus 1 times by x minus 1 will be our simplified version of the polynomial. Moving over with this section, I talked about special cases from the beginning of this video. When I talk about special cases involves polynomials such that they may have only 2 terms. You got x squared minus 9 and x squared minus 25, and I'll just do x squared minus 49. Now, there are special names for these kind of polynomials, and those names involve the difference of perfect squares. Squares should be a type of algorithm that you want to apply to these kind of terms. X squared minus 9 can also be rewritten as x squared minus 3 squared. The word difference means subtraction, and perfect squares means that you have anything that with the 2 as an exponent. So if there exists such a polynomial like this, then there's a specific type of framework that you need to apply. It's not that hard. X and 3 will be copied to both of the terms. What's different about the inside of parentheses is that this is a plus sign and that's a minus sign. And we can confirm that this is actually the correct answer by foiling out. X times x is x squared. X times negative 3 is negative 3x. The inside, 3 times x is plus 3x. The outside, 3 times negative 3 is negative 9. The middle terms cancels out, giving you x squared minus 9, which is exactly what we have at the beginning. So granted that if you're able to rewrite polynomials in its difference of perfect squares, then you essentially have the golden key to use the framework. X squared minus 25 can be rewritten as x squared minus 5 squared. And therefore, if we see that this is considered to be a difference of perfect squares, so difference of perfect squares, then I can use the algorithm, which is going to be x plus 5 and x minus 5. So x and 5 are copied from both of the parentheses, separated by the plus and a minus sign. So the same thing goes for x squared minus 49. Got x squared minus 7 squared. 49 can be expressed as 7 to the second power. And the fact that we can see that this is a difference of perfect squares, I can rewrite it as x plus 7 and x minus 7. Moving along with the difference of perfect squares, sometimes it might not be as convenient as terms to see right away that you can factor out using the special case. I'll write something like this. 4x squared minus 25 and 16x squared minus 1. You can also treat these as difference of perfect squares. It's a little bit hard to see, but the more that you practice on this kind of information, then it should be pretty easy and fun for you to see what's going on. 4x squared, that's the same thing as 2 times x, separated by the minus sign, 5 times 5. It seems like they duplicate twice, 2, x, and then 5. That means I can rewrite this as 2 squared, x squared, minus 5 squared. And then we have the framework, because this is considered to be a difference of perfect square. We see that it means 2x, like 2x, so 2x squared minus 5 squared. And therefore we have the framework to write it as 2x minus 5 and 2x plus 5. When you FOIL this out, you will see that you will get back the original question for x squared minus 25. Same thing goes with questions like 16x squared minus 1. 16x squared can be rewritten as 4x to the second power. Because when you distribute the power 2, 4 times 4 is 16, and then x to the second power is x to the second power. Minus 1 can be written as 1 to the second power. 1 times 1 is 1, which is valid, so therefore we have the framework to use the difference of perfect squares algorithm. We got 4x1, and then we alternate on the signs. You can do plus and minus, or you can do minus and plus. But that's pretty much it. When you FOIL this out, you will get back the original question, 16x squared minus 1. Piggybacking on difference of perfect squares, you will encounter some more complex terms that you need to factor out. So I'll give those out to you. x4 minus 16. x4 can be written as x squared to the second, and 16 can be written as 4 to the second. This is a difference of perfect squares. because I see that x squared is expressed to the second power and 4 is expressed to the second power. So therefore, I can rewrite this as x squared minus 4 and x squared plus 4. Now, you shouldn't stop from here. I can see that x squared minus 4 can be reduced a little bit further out. X squared is the same thing as x to the second power, and 4 is the same thing as 2 to the second power. So this is valid. This is considered a difference of perfect squares, so therefore I have a framework to say x minus 2 and x plus 2. Unfortunately, there is no algorithm for the sums of the perfect squares, so we can't do anything else with x squared plus 4. It just remains x squared plus 4. So therefore, this is the simplified version of x4 minus 16. X to the 4th minus 16 looks a little bit deceptive because there exist two terms, but when you see this on a graph later in the chapter, you will see that there is a lot of complex information regarding just this one polynomial. So that's why we consider this as the simplified version. Moving forward, let's say I have terms like 100x squared minus 16. I can rewrite 100x squared as 10 times x, or just 10x to the second power. 16 can be written as 4 to the second power. This is the framework to give us the difference of perfect squares, so therefore I can rewrite this as 10x minus 4 and 10x plus 4. Let's not stop there. 10x and 4 are both even numbers, so I can pull out a 2. And from here, 2 times 5 will give us 10, so I'm going to put 5. And then 2 times 2 will give us 4. And the same thing can be done with the 10x plus 4. I can pull out a 2 and then multiply 2 times 5 to give us 10. And then 2 times 2 to give us 4. 2 times 2 is 4. And therefore, I have 5x minus 2 and 5x plus 2. That is my final answer. Moving forward, let's say that I have a question such as 25x to the second minus 36. I can rewrite 25x to the second as 5 times 5, so just 5. Then x to the second is x times x, or just x. This is second, and 36 is the same thing as 6 to the second power. This is the framework to give us the difference of perfect squares, So therefore, I have the algorithm to utilize 5x minus 6 and 5x plus 6. There's nothing else I can go from here to simplify further, so this is considered to my final answer. By foiling, you will see that everything should simplify back to give us 25x squared minus 36.